Students, welcome to today's lectures on the course titled Engineering Geology. Engineering Geology. Engineering Geology and Basic Soil Mechanics. So today we're going to look at the nature and properties of soil. Looking at this, we've used the first two videos to treat engineering geology, and now we want to start with the second part of this course titled Basic Soil Mechanics. So under this basic soil mechanics, we will be looking at the topic nature and properties of soil. Nature and properties of soil. So the first thing we have to look at is we want to look at mass and volume related symbols. We need to define mass and volume related symbols such as M, where M is equal to total mass of the soil or sample. Here we have MS, the mass of solids, and by this we mean dry mass. That is excluding void. Then we have mass of water, which is MW. This is mass of water. So whenever you see this, MW is mass of water, and mass of air is MA. M subscript A, call it mass of air. Then we also have the V. This is total volume of the soil, and we have VS. This is volume of solids. Then we have VV. This is volume of voids. We have VA equal to volume of air. Then let me talk about VV. Finally we have to look at VW, which is volume of water, because VV is equal to VW plus VA, as volume of void is equal to volume of water plus volume of air. So, and also V is equal to the total volume is equal to volume of solids plus volume of void. So these are the basic mass and volume related symbols. So the next thing we have to look at is the definition of soil mechanics. Let's define soil mechanics. Definition of soil mechanics. Okay, and this. So according to Carl Tazagi, the father of soil mechanics, he defined soil mechanics as the application of the law of mechanics and hydraulics to engineering problems dealing with sediment and other unconsolidated accumulations of solid particles produced by the mechanical and chemical disintegration of rocks, regardless of whether or not they contain an admixture of organic constituents. So here we have talked about engineering application. We said it's an engineering application of mechanics and hydraulics. So when we apply mechanics, the laws of mechanics and laws of hydraulics to engineering problems, and what are these problems relating to weathered rocks? Remember we talked about disintegration of rocks caused by agent of denudations, and we talked about different type of rocks, igneous, sedimentary, and then metamorphic type of rocks. So we talked about it under the first part of the course, engineering geology. So when we apply the laws of mechanics and hydraulics to engineering problem related with sediments and other unconsolidated accumulation of solid particles produced by mechanical and chemical weathering or disintegration of rocks. So we call this soil mechanics. So we will start with soil properties. And when we talk about the soil properties, we want to investigate soil properties. So now soil properties. The soil mass usually consists of a solid particle with spaces of void in between. So when we have a soil mass, this is a total mass of soil. We expect that it should have solid particles. To have solid particles, so it should have solid particles. The particles may be of different sizes, bigger. Let's see what we have here. So smaller particles, because the sizes are not expected to be equal. So we have bigger and smaller, then we still have the spaces in between this big and the small particles occupied by void. So this void space can be filled by water plus air. So while this one is a volume of solid, call it volume of solid, volume of solids, while this one is volume of void space. So we're going to look at the relationship between this. How do we define this thing? How do we express them in terms of the relationship? So here we have talked about the voids occupying this. You said this void is occupied by water and air, while the other one is by solids. So if we draw a three-phase relationship, we can draw a three-phase relationship to illustrate what we are talking about from here. Okay, without learning it, we can draw a three-phase relationship, which is still use a straight line to do that. So let's see if we can do that. A three-phase relationship. Okay, so we'll have this, first phase, second phase, and we'll have the third. So here we'll have, trying to look at soil as consisting of the first one here. Let's say this, or let's make this very one, let's make it bigger, because solid occupy most of the spaces. So here we'll have this. So we'll call this, let's say this is air. Spaces occupied by air. The total spaces of space occupied by water. Then we have this one is occupied by the solids. So if we look at this, we will see that we can establish relationships based on this. So here, we have here. So here we can call this, and also express the total of all this as the volume of the soil sample. Call this the volume of the soil sample, which is denoted by capital V. Then here we'll call this one volume of air. We'll call this volume of water. Call this one volume of solids. And these two collectively, we can call these two collectively. We can call them. Let's make it later. So you see that here we have between here and here we have what we call between here and here. Okay, so between here and here is the volume occupied by air and water collectively make up what we call VV. That is volume of void. So these two collectively make up VV. As this and this make up volume of void. So this is VV, while this is VA, VW. So we add the three, or this plus this volume of void plus volume of solid, whatever is remaining here, gives us the total volume. So we can call this the volume of solid. This portion is taken over by volume of solid, so call this is still VS. So here we can say, we already established that before, we can say that VA plus VW is equal to VV, and we can say that VV plus VS is equal to V. So these are the basic relationships we can establish. Then we can also say, in terms of mass, if the whole thing is total mass M, then that of air, total mass will be equal to mass of solid plus mass of void, which is the mass of water plus mass of air. So that is what we have here. So that's it. So the next thing we need to look at, all these, we call these constituents of soil. The next thing we need to look at now is to define some parameters like void ratio and porosity. So let's define them. Wipe the board first of all. We'll do that. Stop some wipe this. So I'll create some spaces for calculation and our expressions. So here we have, first thing we have to look at is void ratio. So when we talk about void ratio, we say it compares the volume or the ratio of the volume of the voids to that of the volume of the solids of the soil. So how do we represent it? Ratio. So when we say ratio, we're talking about the volume of the voids. And remember, we say volume of voids is VV over volume of solids. So call this our equation 1. So that's our void ratio. That is volume of voids to volume of the soil or solid of the soil. And then the next thing we have to look at is the second one, which is porosity. So here the porosity is represented, the void ratio is denoted by E. Porosity is N. So for porosity, it refers to the ratio of the volume of voids to the volume of the soil sample. We said the ratio of the volume of voids to the bulk volume of the soil sample. So it's no longer that of the solids. So here we're talking about porosity and in the ratio of volume of voids to the total volume of the soil sample, the bulk volume. So how do we express these two things? Let's see how the relationship between the void ratio and porosity. So here we have, we said N is equal to VV over V. So it means that it follows that 1 over N, if we invert, then we'll have this is equal to V over VV, V over VV. And remember that we've said today that VV, but we can say but V is equal to VV plus VS. V is equal to VV plus VS, volume of void plus volume of solids. So if we have this, it means we can come here and say, we can still write is equal to, here we have V now is VV plus VS over VV. This is equal to, let's circle this so that it doesn't confuse us. This here, so here we have VV plus VS over VV. So here we can still see VV over, this is something as VV over VV plus VS over VV. So this will cancel this cancels this to give us 1. So we'll have our 1 over N is equal to 1 plus VS over VV. Okay, and remember that E, I can also say but E, we have seen it here already, E is equal to VV over VS. So it means VS over VV is equal to 1 over E. That's what it means, because if E is VV over VS, then 1 over E will be equal to the reverse, which is VS over VV. So we'll carry this and come here, since we know that this is the reverse. What we now have is 1 over N will be equal to 1 plus, we will have 1 over E, because it is the reverse of this. So VS over VV. So this will be, it means, what do we do? Let's, the common LCM is E over E in 1, now here is E plus 1 over E. So this is what we'll have. We'll have our 1 over N is equal to E plus 1 over E. So, and our N, which is our porosity, will now be equal to E over E plus 1. So this becomes our third equation, because this one is the second equation, equation 2. So this becomes our equation 3. So this is the relationship between void ratio and porosity. You can also go ahead and express the void ratio in terms of the porosity, because this is porosity in terms of void ratio. So let's see how we can do that. Here, let's wipe the board. I'm able to have enough space to do that. Okay. So now we have, so this is total volume. So now we want to express this in terms of that. We said N is equal to PV over V. So here our E will be equal to, we have VV over VS, VV over VS. So here we have, remember that VV over VS is our void ratio, while this is our porosity. So all we need to do in terms of that is that we have our VS, we can reverse this, then we say 1 over E will be equal to VS over VV, and reverse it, 1 over E VS over VV. So, and then we know that VS, volume of solid, will be equal to, because we said that V is equal to VV over VS. So it means here VS should be equal to V minus VV. So bring it here. So now this is the same thing as V minus VV over VV. So if we express this, this can still be equal to V over VV minus VV over VV. So this will cancel this to give us 1. Plus 1, so we'll have 1 over E will be equal to, here we'll have V over VV is, okay, minus, this is 1, minus 1. So, and this will still equal to the LCM here, is still 1, so we'll have V minus VV. Okay, so now let's wipe this off. So we have this is equal to 1. Remember that we said that porosity is V. Porosity is V from our first this expression, initial expression, our equation 2. We said that since we have 1 over E is equal to V over VV minus 1, it means that we can say 1 over E is equal to, because this is the reverse, when you reverse this, you have this, so it's going to be 1 over N, because V over VV is 1 over N, because N is VV over V, so when you reverse it, it becomes 1 over N, which is V over VV minus 1. So we can still find LCM here. We have, it will be 1 minus N over N. That's what it means here. I said that 1 over E is equal to 1 minus N over N. It follows that E is equal to N over 1 minus N. So that is our fourth equation, equation IV. Fourth equation. So it means from our various equations, we can now conclude that gotten our first, second, third, fourth, and 5th equations. So here, this is equation 1, this one is equation 2, equation 3, then the relationship is N is equal to E over E plus 1 is the equation 3. We'll have the fourth one, where we set E is equal to N over 1 minus N. This becomes our fourth equation. So this is the relationship between void ratio and porosity under soil properties. The next thing we're going to look at is the degree of saturation. So let's wipe this out so that we can continue with it. So talking about soil mechanics. So we'll continue with degree of saturation. Degree of saturation. Okay. So what do we define it as? We said degree of saturation refers to the proportion by percentage of water present in a given void volume in the soil. So the proportion of percentage of water. A soil is referred to as dry if only air is present in the void volume, whereas the soil is said to be saturated if only water is present in the entire void volume. Thus, the soil is partially saturated if the void volume contains both air and water. So what we're trying to say here is that the degree of saturation. Remember we said for every soil sample, if this is a soil sample, remember we said there are particles. These are the solid particles, solids. We call the other ones, the smaller spaces here are being filled up by, this one is void, which is air plus water. So if this void is equal to air throughout, it is dry. It is dry. It's equal to dry. Then if the void is filled up with water, then it is said to be saturated. Then if void contains air plus water, then it is said to be partially saturated. So we should note this. So degree of saturation. Okay. So a degree of saturation is given by, we call it S script R, is given by the volume of water over volume of voids. So S script R is equal to volume of water to volume of voids. Remember, the volume of water is denoted by VW over VV. So when we express this in 100%, we're talking about degree of saturation. So this is our equation 5. So we can also say that degree of saturation is equal to WGS over E. It is given by WGS, which is the weight of the soil multiplied by specific gravity over our void ratio. So then the next thing we need to look at is our percentage air void. So percentage air void, and this is denoted by N subscript A. So percentage air void refers to the ratio of the volume of air to the total volume. So we're talking about NA is the volume of air over the total volume. Express it in 100% of ground percentage, so 100%. So this becomes our equation 6 VI The next thing we look at is the air contents. So this is D. Look at E, call it the air contents. Air content is given by AC and is defined as the ratio of the volume of air to the volume of voids. The ratio, so called AC, ratio of volume of air to the volume of air to volume of voids. So it is also a percentage, so we have to multiply by 100%. So this is also our equation VII, our equation 7. So here we have AC, you can also call it the air contents. AC is equal to 1 minus the degree of saturation. So 1 minus that times 100%. So for saturated soil, both air content and percentage air voids are 0. So when it's saturated, it means the volume of air has been displaced by water. So that is it. So the next thing we look at particle specific gravity, GS. Call it particle specific gravity. We call this GS. Particle specific gravity compares the weight or mass of a given volume of material with the weight or mass of equal volume of water. Long as we define specific gravity of any body or any material as the weight of that material, the mass of that material, to the equivalent of water, of that of water. When we compare that of the material with that of water, we call it specific gravity. So we express it as GS. S here is equal to mass of the solid over mass of water, and or we do it as weight of solid over weight of water. And we can also call it rho, which is density of solid over density of water. So we'll call this our equation VII8. So we'll call it 8a. This is equation 8a. Then we can also express the specific gravity as the mass of solid, mass of water will be the volume of water times density of water. Remember that we said density equal to mass over volume. So it means mass of water. So it means that density of water is equal to mass of water over volume of water. So we can do this. So here we have, we can say mass of water is equal to density times volume of water. So it means MW is equal to density of water is this multiplied by the volume of water. So it means GS is equal to, I can also express it in terms of weight of solids over density of solids multiplied by the volume of water. So weight of solids multiplied by the density of water by the volume of water. So this forms our equation 8b. What is our equation 8b? So where we can call that where this and this density and unit weight of water respectively, or the density and unit weight of water respectively. Okay, so the next thing we look at water or moisture content. Call this water or moisture content, and we denote this by W. So we're talking about water or moisture content. We said this refers to the ratio of amount of water present in a soil to the amount of dry soil. It is usually expressed in terms of percentage. Moisture content is represented mathematically as talk about the mass of water to the mass of the dry air. But most times when you collect soil sample, put it up in an oven, heat it until you have a constant weight. That's when the water must have been expelled. Then the amount of water expelled over the amount of the dry mass of the soil gives you, when you express it in percentage, gives you moisture content. You do that under your practicals. You do moisture content tests in the lab with a practical instructor or a practical instructor. So here we said mathematically the moisture content W is equal to the weight of water over the weight of solids, and this will be equal to W over Ws. So this one is our equation 9, X. So, or we can say is mass of water over mass of solids, and this is equal to MW over MS. So this, let's call this IXA, equation 9A. This one is equation IXB, 9B. So the next thing we look at is the unit weight of soil. Unit weight of soil. So we denote this by this. So which is gamma. The unit weight of the soil refers to as the weight by unit volume. Major soil unit weights are given. So when we talk about the mass of the soil or weight of this weight by unit volume. So what we call bulk unit weights. Let's look at the bulk unit weights. Bulk unit weights, which is denoted by gamma B, is equal to total weight over total volume. And this is equal to W over V. And when we want to express this, it becomes the weight of solids plus weight of water over volume of solids plus volume of water. Then if you want to express this in another form, this becomes gamma B is equal to GX VS. We want to express it in unit weights. It becomes GS, where this is the unit weight multiplied by the volume of solids by the unit weight of water plus the volume of void unit weight of water by the degree of saturation. So this over volume of solid plus volume of void. So we can also express this because if we look at this, we know what is common. See that this is common. Where we see that gamma W, bring it outside. What else is outside is common. That one thing is common. So we bring it out. We have GS, VS plus we have V, we have VV, SR over VS plus VV, VS plus VV. That's what we have. So we'll call this our equation 10. Equation X is our equation 10. So we'll talk about bulk unit weight. We want to look at saturated unit weight. Our saturated unit weight, which is our gamma sat. How do we express it? Saturated weight over total volume. And if we express this, our gamma sat will be equal to gamma W into the water. We open our brackets, multiply by specific weight plus our void ratio over 1 plus our void ratio. So this becomes our equation 10b, xb, and that one is xa. Now the dry unit weight will be equal to, here we say gamma D will be equal to dry weight over the total volume, and our gamma D dry unit weight will be equal to gamma W specific unit weight over 1 plus E. This is our equation XC, 10C. So the next thing we have to look at is our submerged unit weight. Our submerged unit weight, we call this one submerged unit weight. Submerged unit weight. So under our submerged unit weight, here we have gamma W sub, gamma sub will be equal to saturated unit weight, which is our gamma sat minus the unit weight of water, That's what we have, which is gamma W. So gamma sub will be equal to, I will have unit weight, the gamma W multiplied by G of solids, weight of solid minus 1 over 1 plus void ratio. Yes, this is our equation XT 10G. For the density of the soil, that's the next thing we want to look at. The density of the soil is soil, which is referred to as its mass per unit volume. So when we talk about density, we say mass per unit volume, but we're going to look at bulk density bulk density. We'll have rho B equal to total mass over total volume. So this will be equal to mass over volume, and the overall mass is mass of solid plus mass of water over volume of solid plus volume of water. So that is our bulk density. Let's also express the bulk density using other expressions. So here, first of all, wipe the board. Okay. So our bulk density can be equal to specific unit weight of solid multiplied by volume of solid times density of water plus volume of void, density of water, saturated, degree of saturation, express this over the volume of water of solid plus volume of water. So this is what we have, because when we're talking about mass of solid, it is, why we have this is mass of solid, because all these represents ms, mass of solid, and all these represents mass of water. That's what it denotes. So we have this. We can simplify it in such a way that our will be what is common in these two. See that rho W is common, so bring it out. I have GS plus PV SR over Vs plus Vw. So this can also be equal to W bracket GS plus VSR over plus the brackets over 1 plus E. So this is our equation 11a. The next thing we look at saturated density. Look at saturated density, and which is OSAT will be equal to density of water. We have GS plus E over 1 plus E. So this is our equation 11 of X I B. The next thing we look at is dry density. Out of our dry density, which is rho D. This will be equal to mass of solids over mass of the total volume. Gross density is always mass over volume, total volume, and this will be equal to mass of solid, density of water, which is the density of solid, over 1 plus E. So we said rho B bulk density over 1 plus W. So this is our equation X I C 11C. Then we now look at submerged density, which is rho sub equal to density of water by specific gravity of solid minus 1 over 1 plus E. So this becomes our equation X I D 11D. So these are the various expressions we are having based on densities we're able to express this relationship. So in the next video, we will look at sieve analysis, consistency of clay soil, and we're going to also look at plasticity, liquidity, and consistency indices. So when we look at this, plasticity, liquidity, and consistency indices. So after doing that, we will perform example calculations based on the various equations we've been able to derive. Thanks for being part of this video. If you're here to subscribe, hit the subscribe button, turn on the notification icon to receive updates whenever we post videos on engineering, geology, and basic soil mechanics. Bye for now.